So here's an example of a synoptic question, a really good one actually, where they've asked you to do an evaluation first, then they're talking about Hubble's law, then they're talking about individual stars, then they're talking about radioactive decay, and lastly they're talking about an exponential function. So there's loads of different skills all in one question. Now actually this is the point where this is quite a lot of marks for one question. And if you sort of, I didn't get that, and you sort of jump out at the start of the question and you don't sort of pick up marks as you go through this hard question, then you're going to struggle and you're going to lose a lot of marks. So you've got to be really resilient. And if you didn't get one part of it, don't give up on the whole question. Just pause, think, well, okay, where can I pick up marks in this part, and in this part? Okay, so about 100 years ago, first measurement spectra from galaxies beyond the Milky Way were made. Okay, so that was Hubble. Wavelengths of the spectral lines were observed and shifted, and Hubble discovered a rough correlation between the shift in the spectral line and the distance to the galaxy. So here's distance to the galaxy, here's the shift in the wavelength, which is proportional to the redshift, essentially. Okay, so he was saying then that the further away they were, the more redshifted they were. This is his 1929 data, and then they've given us the data that he had in 1931. So the question's going to ask us about this. Again, it's not really about explaining Hubble's law, it's about the quality of the data, first of all. So let's read the question. The question used by Hubble for this 1929 plot is contained within the rectangle close to the origin in the 1931. So let's go find that, to understand that. Oh yeah, wow, okay, so actually this data, all of this data could fit in there. So obviously in the 2 years after here to here, he went and found some much more distant galaxies and did the same type of observation on them. You can see there's a difference between the two correlations. Explain how Hubble's observations support the conclusion the universe is expanding. Okay, that's my first thing I need to do. And 2, assess the reliability of this conclusion on the basis of Hubble's original data. Right, so it's 5 marks, but really, if you like, it's a 2-mark question and then another 3-mark question. So how do Hubble's observations support the conclusion the universe is expanding? Well, firstly, let's state what the trend is. So further away, let's use better language than that, more distant galaxies show a greater change in wavelength. Now notice I've not said redshift because I'm using the data. Now we could have plotted redshift on that axis, but it's not, it's change in wavelength. So I'm just going to stick with the evidence I've got. Okay, so that's my first point. Okay, this supports the idea that they're more redshifted, so that supports the idea that they're moving faster away. Their recessional velocity is greater, and you'll be used to seeing that graph with recessional velocity on that y-axis. Okay, and redshift is actually defined in your equation here as delta lambda over lambda, okay, which is roughly equal to the change in frequency over frequency, roughly equal to the change in speed over original speed. So this is the definition though. You don't really need to plug this in, but I'm just going to do that because I think that's thorough. Okay, so redshift Z is delta lambda over lambda. We've not been told lambda, but for each, if the delta lambda is bigger, then obviously the redshift is going to be bigger as well, which infers that they are moving faster away from us. Should I say Earth? Why not? That's where he was when he measured. Okay, so that's my first thing done. I think I've a pretty good explanation of how his observations support the conclusion. Right, but now what's the reliability of the conclusion on the basis of Hubble's original data set? Well, let's have a little look at the data set. Right, well, it's not a very precise set of data in that they aren't all sitting on that line. So there's quite a lot of scatter. It's not very precise. So that's my first bit when I'm talking about the reliability. So Hubble's 1929 data shows a large amount of scatter from the line of best fit. Okay, that's a good point there. And also, well, compared to the 1931 data, we're only going a very short distance, aren't we? It's only, it must be only like a 10th or a 20th of the distances they managed to measure in the future. So the independent variable, has a small range, and the marks for saying a small range of distances. For which he was able to measure the redshift or the delta lambda. Okay, so then just some statement really that from the original data the conclusion's not very sound. It's not very reliable. I don't want to say spurious. In the mark scheme they've used the word, it's quite speculative. I guess he had his hunch, he wanted to publish it, and then he wanted to carry on and find that detail, find that extra data to confirm his ideas. So the light emitted from a star is due to the energy released by fusion reactions taking place in the core of the star. Our sun is a main sequence star with a luminosity of this. So luminosity is the power emitted essentially at the point source. So an analysis of the sun spectrum gives a lambda max of this in nanometers. So I'm straight away going to get rid of my prefix because that's just good habits for exams. Use the data provided to calculate the radius of the sun. Alright, so I'm going to go ahead and go to my space section. Well, not really actually, I'm going to go to my thermodynamics section because that's where these two equations are. Firstly, this one is going to allow me to work out temperature, and then this equation here, the same equation but here area is replaced with 4 pi r squared. So this equation links the radius and the temperature with the Stefan-Boltzmann constant. You can remember that, and that's in the formula sheet at the front. So I'm going to use this to give me T, and then that to give me that. So scribble those ones down. And that's a unit. MK is the unit, so I really need, it's meters Kelvin. Okay, so I don't need to worry about that. It's not millikelvin, which you might get confused on the formula sheet. And then the next one is the Stefan-Boltzmann law. Let's do this bit first then. T is that over lambda max. I think I'll just do that one straight away. 5773 Kelvin, and that's sensible order of magnitude in the thousands of degrees Kelvin for the surface of the sun. Okay, or over the star. Now I've got this, I just need to go ahead and find sigma, which is from the data sheet. Stefan-Boltzmann constant there, look, sigma 5.67 times 10 to the minus 8. Rearrange this for r, why not? L over 4 pi sigma t to the fourth rooted is r. Now I can put my numbers in. L. And then root all that. 6.97 times 10 to the 8 meters. Okay, so some information about the sun. 4.5 billion years old. Determine this, scientists measure the ratios of lead isotopes found in meteorites. Since uranium undergoes radioactive decay in a chain to eventually become an isotope of lead, the ratios of lead isotopes can be used to find the age of a meteorite. Fair enough. So this decays to this, 238 uranium to 206 lead, by the emission of alpha and beta minus. Okay, so let's just remind ourselves alpha's 4 and 2, and beta minus is 0 minus 1. In the transition of uranium-238 to lead-206, 8 alpha decays must occur. So actually, I thought at first I was going to have to actually work that out, which I could have done. So there's 8 lots of 4, 2 alpha. State the number of betas that must occur. So there is a number of betas. What's that going to be? Well, let's balance it all up. 238 to 206, that is 32. 32 divided by 4 is 8. So that's how I would have worked that first one out. This number should therefore have changed by 16. It has only changed by 10, so there must be 6 here. Okay, I hope that makes sense, really. I don't think that's a difficult question. In fact, this chain was in the new GCSE as one of the challenging questions in the GCSE, but they were asked in the new GCSE textbook to go ahead and work out every step, or they were told this has 8 alphas and 6 betas, and the order, and they had to go through every single step. So I don't think this should be hard for you. In fact, I think if you see this type of thing, you should be thinking, right, easy marks to get. Thank you very much for the 2 marks there. One isotope in the chain is thorium-230, which decays into an isotope of radium with a half-life of 75,000 years. Calculate the time in years it would take for 90% of initial sample of thorium to have decayed. 90% is 0.9, or in other words, the current number that there are left is 0.1 N0. Okay, so now we can use our normal equation for decay. Where did I get that from? Well, the radioactivity part of the nuclear radiation, radioactive decay. Here we go. Right, okay. We haven't got lambda, but we do have half-life, and you can always convert between the decay constant lambda and half-life. If you've got a half-life, then you have got the decay constant, because they are inverse one another with the factor ln2. So that is what that equation there states. The decay constant is ln2 over the half-life, and you can therefore just work in whatever units you've got. So we can insert our definition of what n is here for our equation. And you can notice now the n naughts cancel, so I get 0.1 e to the minus lambda t. To get access to them, I think I need to take the natural logs of both sides, and now it's a simple rearrange for t. So ln 0.1 over minus 9.2, sorry, don't really need the negative really because it's scalar. 242 times 10 to the minus 6 is t. So ln 0.1 over the previous answer gives me 249,000 years. Okay, which is 2.5 times 10 to the 5. Considering they've given me 2 sig figs. Okay, hope that makes sense. Once you've practiced these, that bit becomes a bit of second nature, and you can probably go straight to this point here. I think it's worth showing you where that cancellation is, so you can recognise I've got a percentage. I don't need to be told what my initial value was, because I know it's a certain percentage of n0, and eventually the n0s just cancel here. Okay, and the other thing to remember is if you know lambda or you know t1/2, you know the other one. Okay, hope that was helpful to you. I've been Kit Best Masters. Thanks a lot for watching Guerrilla Physics. So the A-star questions are going to be where your good exam technique comes into play, and this is where a lot of practice at exam questions is good. But remember, each individual part can be answered independently, so make sure that you're resilient enough to pick up marks on the last few questions in your exam papers. They're going to be really, really hard. They're going to be asking you about really difficult context, but you can do it, and importantly, make sure you're picking up a good proportion of those marks.